Hey everyone, welcome back to probability theory. This will be lecture 9 of the course. And in this section, we're going to go through the law of total probability and Bayes' rule. So let's go ahead and jump into it. And we'll call this section 1.9, the law of total probability and Bayes' rule. All right, so we'll start by, first we'll kind of set up a couple of definitions that we need for the law of total probability. Then we'll state the law of total probability, and from that, it's a quick jump to Bayes' rule. And then after we get through all those three pieces, then we'll do some examples. So let's start by defining what we mean by a partition. That's a very important component here. Okay, so we say that the collection of sets, and we'll say B1, B2, so on up to BK, K being some positive integer, obviously. The collection of sets B1 through BK is a partition of S if, S being like kind of the universe or the sample space in the context of probability, we say that this is a partition of S if two things are true. The first, S needs to be equal to the union of all these sets, B1 or B2 or ... or BK. So the union of this collection of sets is equal to the entire space. And second, the intersection of two arbitrary sets in this collection, Bi and Bj, is empty. And this is going to be for any I not equal to j. Okay, and so this is what we mean by a partition. Okay, so basically it's just a collection of subsets of a space which, taken together, the union of them, is equal to the entirety of the space. And the intersection of any two subsets is empty, so disjoint. So B1 through BK are disjoint sets that collectively exhaust the space S. Right, so you can draw a nice picture, like let's say we have B1, B2, B3. So let's consider B1, B2, B3. Then we could say these partition a space S. So let's draw the space S. Here's this rectangle. And any breaking up of this space into disjoint subsets, B1, B2, B3, gives you your partition idea, right? So it could look like that, obviously. It doesn't have to look like that. It could look like anything. Right? It could be like this. Right? The key idea with a partition is just that it breaks the entirety of the space up, right? So there's no part of S that isn't in B1, B2, or B3. And also there's no overlap. So notice the way we've drawn this, there's no overlapping subsets. Okay, and so that is the idea of a partition. Now, this will come up when we get into the proof of the law of total probability, but it is nice to kind of lay this out ahead of time, just because this is sort of a key idea when describing the law of total probability. So notice that for any subset A of a space S that has a partition B1, B2, B3, we'll start with 3. This is true for any number of subsets though. So notice that for any subset A of a space S that has a partition B1, B2, B3 on it, okay, I'm going to draw the picture first, and then it'll be very obvious what I'm trying to get to here. So we'll start with the picture here. So again, this is kind of the same space, right? And we've got this partition B1, B2, B3 on it, which I'll just draw like this. Now I've got an arbitrary subset in here and we'll call that set A, right? So A is kind of like just in the space here. Now notice that A can be thought of as, this piece here, which is A and B1, right? And then this piece here in the middle is A and B2. And then, of course, over here you've got A and B3, right? So you're just taking, the different pieces of the set A and noting which part of the partition that lies in. Now notice this part here only lies inside of the B1 partition. It doesn't, because B1, B2, B3 are all mutually exclusive, you don't have a situation where a piece of A is laying in two sections, right? It's always only in one, right? And so that being the case, the subset A can be written in a unique way. So we can write A as being equal to A and B1, right? Namely this piece here, or A and B2, middle piece here, or this right-hand side piece, A and B3. Okay, and so it doesn't take a whole lot of, you can kind of picture how this could be expanded into, a larger space with more complex partition, and maybe, A, doesn't necessarily land in every subset of the partition, just a subset of that subsets of partitions. But you can kind of see how this could be expanded, right? You've got just some other set that's kind of in here that's not part of the partition necessarily, but overlaps the partition because it's a partition. Okay, and so this idea will be used in the law of total probability. This isn't the law of total probability, but it's used in. It's used in the law of total probability. And so it's nice to just kind of spend a minute drawing it out and making sure that you can visually see it. Okay. All right. So with that, then let's go ahead and state the law of total probability next. Okay. And so it's a pretty straightforward theorem once you have that picture in mind. Okay. So this is the law of total probability. Okay, and so here we go. Let's assume that B1, B2, BK, that's a B. So assume this set of subsets of S is a partition of S. Okay, and so of course, when we say it's a partition of S, what we mean is the previous definition, right? So you've got this partition of S, and remember, just to keep in mind what that means is that the union of these sets here is equal to the space S, and these sets B1 through BK are all mutually exclusive, meaning they don't overlap. Okay, so assume this is the case, and that the probability of any one of these, BI, is greater than 0. Okay, and it's greater than 0 for any one of these i's. I equals 1, 2, ... Okay, right? So the probability is greater than 0 for each of these. So meaning that none of these sets are empty, basically. Okay, so then for any event A in S, here's what we've got. This is the law of total probability. The law of total probability says the probability of A is equal to the probability of A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2 plus ... plus the probability of A given BK times the probability of BK. And then, of course, this can be written out much more succinctly using sigma notation as the sum from I equals 1 up to k of the probability of A given BI times the probability of BI. Okay? And so the probability of any event A can be understood as understood in terms of this union, right? And basically the additive law, right? Well, additive law and multiplicative law are kind of at work here in the background. And so let's talk through, I think the proof will come really quickly because we've seen the picture, but let's talk through the proof of this. Okay, now remember what we just talked about is the subset A can be written as this big union. So the subset A can be written as, well, we know A is equal to A and S, of course. And we know that S is equal to B1 is equal to this partition, the union of this partition, B1 or B2 or ... or BK, right? And then just doing some set operations here, we can see that this is equal to A and B1 or A and B2 or, well, ... or A and BK. Okay, so this is the picture that we drew on the previous page. All right, here we're just extending it to some general K, but it's the same exact idea. Same exact idea. Now, because this B1 through BK is a partition, so because B1 through BK is a partition of S, we know that the intersection of B1 and B2, for example, is empty, and the intersection of B1 and B3 is empty. And so any two arbitrary members of this collection of subsets are going to have an empty intersection. And so that means that A and BI intersecting A and BJ must also be empty, right? Anytime I is not equal to j. Right, because if BI and BJ are empty, then A and BI and A and BJ must also be empty. Right? These two don't overlap, so obviously the intersections of these two with any other set must not overlap either. Okay, so the intersections are all empty, and therefore A and BI and A and BJ are mutually exclusive events. Okay, so that's great. So now what we can do is we can come back up to this piece here and let's figure out what the probability is of this. So the probability of A is equal to the probability of A and B1 plus the probability of A and B2 plus ... plus probability of A and BK. Okay, so we've got that. And so that's just the additive rule, the additive law of probability, right? And so then we can break each of these down using the multiplicative law. Now these are not mutually exclusive, right? A and B1, they intersect, right? So we have to consider the conditional probabilities here. But this could be written as the probability of A given B1 times the probability of B1. This could be written as the probability of A given B2 times the probability of B2. And finally, this can be written as the probability of A given BK times the probability of BK. Well, of course, that is just the sum that we stated in the theorem. So this is just equal to the sum from I equals 1 to k of the probability of A given BI times the probability of BI. Right, and so that's the theorem. This is really just, this all kind of just falls out of this characterization here. So you've got a partition, and then any subset can be written in this clever way using the partition. Okay, and so that is the law of total probability. Now, so the usefulness of this, well, it's very useful, but the biggest use case is Bayes' rule. And so in the examples that we're going to look at in a second, we'll see that it's oftentimes much easier to calculate the conditional probability of like A given BI if you choose BI well than it is to compute the probability of A directly, right? And so this is where the idea of Bayes' rule comes from. So let's state that next. Bayes' rule. Okay, and so what does this say? So assume that B1, B2 through BK, collection of subsets of a space S is a partition of S. All right, it's a partition of S such that the probability of BI is greater than 0 for all I. Okay, so I 1 through K. Just meaning that, you know, this partition is like sort of an efficient partition in that we don't have a bunch of empty sets in here. These are all these sets have something in them, right? Meaning that therefore their probability is greater than 0. Okay, then here's Bayes' rule. Here's what it says. Okay, Bayes' rule says that the probability of B sub j given A, right? So the probability of one of these events given A is equal to the probability of A given Bj times the probability of Bj, all divided by, now this is the total law of total probability in the denominator here, where it's a sum from I equals 1 up to K of the probability of A given Bi times the probability of Bi. Now notice these are J's up here and these are I's, so the sum, you know, they're unrelated, obviously. But basically, if I want to know the probability of one of the events in the partition, given some other event A, remember A is kind of the overlapping arbitrary subset, then what I can do is I can identify the probability of A given Bj divided by, or times the probability of Bj, and I can divide it by the total probability of A. Right? And so this seems a little strange at the onset, right? It actually follows very quickly from the law of total probability. Let's walk through the proof quick, and then we'll try to make more sense of this through some examples. So how do we prove this? You'll see it's an immediate consequence. We basically got the law of total probability. What does it say again? Well, it says that the probability of an event A is equal to the sum I equals 1 up to K of the probability of A given Bi times the probability of Bi. Right, so remember that's the law of total probability. Now, the other thing you need here is the definition of conditional probability. So the definition of conditional probability, what does it say? Well, remember it says the probability of A given B is equal to the probability of A and B divided by the probability of B, right? So these are the two things that you need to prove Bayes' rule up here. And so what is Bayes' rule saying? Well, Bayes' rule, what we're interested there in is the probability of Bj given A. Well, just the definition of conditional probability says that this must be equal to the probability of Bj and A divided by the probability of A. Right, and actually, let's write it the other direction. Probability of A and Bj, just like because it's aesthetically nicer to look at, like this. Okay, so you've got that. And this A and Bj, we know, can be just kind of rearranging this definition a little bit for this intersection piece. We know that that's equal to the probability of A given Bj times probability of Bj. So that's the numerator. Now what is the probability of A? Well, it's the law of total probability, right? It's just this. Right, so that's just equal to the sum from I equals 1 up to K of probability of A given Bi times the probability of Bi. Right, and so that's just the way it works, right? So you basically take the law of total probability and the definition of conditional probability and just kind of slamming the two together, you get Bayes' rule. All right, so That's Bayes' rule. Let's do some examples using it so we can kind of see the usefulness here, because this is a very, very powerful theorem, and it's extremely useful, namely why it's powerful. So these examples, I'll read them first and then we'll write them out and digest them. So just reading it out, it says a certain disease affects 1% of the population. A medical test correctly identifies 90% of those people who have it, but it also provides a false positive result for 5% of healthy people. If a person's test comes back positive, what's the probability that they actually have the disease? Okay, this seems straightforward, sort of, but if you think about it, it is kind of a difficult problem to solve if you're not using Bayes' rule. So let's write it out. So a certain disease, affects 1% of the population. Okay. A test identifies 90% of those who have it. So a test, I'll say correctly identifies 90% of those who have the disease. Okay, so if you've got the disease and you take this test, 90% of the time the test is going to mark you as having the disease, right? So it's not infallible, right? But it also provides a false positive. It also provides a false positive for 5% of healthy people. Meaning that, if you don't have the disease, but you take this test, 5% of the time it's going to say you have the disease, right? So this is an example of a false positive. So here's the question. If a person's test comes back positive, what's the probability that they actually have the disease? So if a person's test comes back positive, what is the probability that they actually have the disease? All right, so that's kind of that's the idea. So let's get some symbols into the mix here and some numbers. And so we'll use D to denote the event of having the disease. So this means you have the disease. And we know that the probability of having the disease in the population is given as 1%. Okay. We'll also use the symbol plus to denote the event of a positive test result. And so you can get a positive test result when you have the disease, right? And we're told that that's 90%, so 0.9, right? So if you have the disease and you take the test, you get a positive test result 90% of the time. Now, we also know that there's a false positive, right? So we also know that the probability of a positive result, given that you don't have the disease, so D complement, is 5%. So 5% of the time, 0.05. Right, and so then you can just use a little bit of logic to just, or you can use so you can use 1 minus, right, to identify the probability of negative given that you don't have the disease. So probability of a negative test result given that you don't have the disease is going to be equal to 1 minus the probability of a positive test result given that you don't have the disease, which is 1 minus 0.95 or 1 minus 0.05, which is 0.95. Okay. All right. So this is the information that you can kind of easily get from the statement, right? And so what are we after? What do we want? Well, we want to know if a person's test comes back positive, what's the probability that they actually have the disease? So we want to know the probability that they actually have the disease given a positive test result, right? The test result comes back positive. What's the probability they actually have the disease, right? So that's what we're after, right? And so this is what we want. That's what we're after. So let's remember what Bayes' rule says. This is a custom perfect example for Bayes' rule. Now I'm just going to restate it here so we can see the pattern of how this is all put together. So the probability of B sub j given A is equal to the probability of A given B sub j times the probability of B sub j divided by the total probability, I equals 1 to k, of the probability of A given BI times the probability of BI. Now, so that's Bayes' rule. So we want to use this to solve, we want to use this theorem, but plugging in these actual numbers to solve for the probability of D given plus. All right, so let's just think about it symbolically here. So the probability of D given positive, right? So that's this piece. Well, Bayes' rule says I'm going to figure that out by going probability of positive given that I actually have the disease times the probability that I have the disease. That's the numerator. Now, notice that this guy here is in this sum, right? So A given Bj is in here. J is less than K, so it's one of these, right? So you can immediately just say, okay, that's got to be down here too. And what else is in here? Well, what's changing in this sum? It's not the event A, so the plus is going to stay the same. What's changing is we're going across the partition, right? All of the BI's, I equals 1 through K, right? And so the D is part of the partition. You either have the disease, in which case you've got the D. Otherwise, you've got the complement, right? There's really only two subsets in the partition here. So D is one of them, and D complement is the other. So the other piece in the sum is just the probability of a positive given that you don't have the disease times the probability that you don't have the disease. Does that make sense? Hopefully that's clear. So you've got the whole space, and the partition just looks like this. You've got either you have the disease or you don't have the disease. Okay, and the positive is what overlaps here. Okay. So this is the setup using Bayes' rule, right? So you kind of start by, well, you identify what the conditional probability that you're looking for. In this case, it's D given positive result. And then I usually just say, okay, to start with that, and then like rewrite this numerator we got to flip the conditions, right? So it's B positive given D times the probability of D. And then that goes down here, and then you just think through what the rest of the partition must look like. So in this case, the partition is just either you have the disease or you don't have the disease, right? And then just write them all out. Now, admittedly, like this is a simple setup because the partition is just two subsets, right? It could be more, right? But in this case, it's just two. Okay, so we could take that and we can plug the numbers in. Okay, and so the numerator is 0.9 times 0.01. Right, so this is the probability of a positive test result given you have the disease. Remember, 90% of the time. And this is the probability of actually having the disease, is 1%, right? And so that's going to be down here too. And then what's the probability of a positive result given that you don't have the disease? Right, remember, that's the false positive, so that's 5%. And the probability that you don't have the disease is, well, 99%, right? It's 1% that you have it, 99% that you don't. So you just crank all these numbers out. Up top, you should get 0.009. Down below, you should get 0.0585. And so altogether you get 0.1538. So about a 15% chance. So if you get a positive result, there's about a 15% chance that you actually have the disease, which kind of seems a little bit strange, right? But these tests are not, they're not like perfect, right? Obviously. So you've got a correct identification of 90% for those who actually have it. It's a very rare disease, though, and all of that kind of factors in, and you end up with, hey, look, if you get a positive test result, there's only a 15% chance you actually have this disease. So there you go. So that's an example using Bayes' rule. Let's do another one. The next sort of classic example type is using spam filter, is a spam filter question. So a company uses an email filter that marks messages as spam. A company uses an email filter that marks messages as spam, right? So, you know, an email comes in, it hits the filter, and the filter makes some determination. So what does the filter end up doing? So 4% of all emails are actual spam. That's to start out with. 4% of all emails are actually spam. Okay, so that's like the truth of the matter, right? And so then the filter correctly identifies 95% of spam messages as spam. The filter correctly identifies 95% of spam messages as spam, right? So, you know, you could go through and you could look and, you know, oh, it correctly identified these 95 as spam, but oh, these 5 got through. Okay, so you can just test these things. And then the filter incorrectly marks 2% of non-spam messages as spam. So the filter incorrectly marks 2% of non-spam legitimate messages as spam. So this is like the false positives, right? And we've all seen this, right? You sign up for something and it says check your email, check your inbox, and if you can't find it, look in your spam folder. Right? So this is your spam filter, like false positive, doing false positives on stuff that's legit. So this is kind of the facts of the case, and the question is, if an email is marked as spam, what's the probability that it truly is spam? So if an email is marked as spam, what is the probability that it actually is spam? Right, so what's the probability that if an email is marked as spam, what's the probability that it actually is spam? Okay, so let's, just like before, let's lay out some symbols and get some probabilities on the table. So let's say S is the event that the message is spam. And so the probability of S is 4%. Okay, and let's say plus will denote the filter marks a message as spam. Okay, and so we know the probability of the message getting marked as spam given that the underlying message is spam. We're told that that's 95%. So 95%. And we're also told that the probability of the filter marking something as spam, if it isn't spam, if it's a legitimate message, is only 2%. Okay, and of course, you know, we can also figure out that the probability of something not being spam would be equal to 1 minus probability that it is, which is 1 minus 0.04. So we get like 96% there, right? So The probability that a message isn't spam is 96%. Now, what are we looking for here? So here what we're after is the probability that a message is spam given that it gets the mark from the filter as spam. Right? So the filter says this is spam. What's the probability that it actually is? Okay, so this is what we're after. All right, so let's write this out. So the probability that a message is spam given that it's been marked as spam, well, that's equal to the probability of the filter marking it as spam given that it is spam times the probability that it is spam. That's the numerator. Remember, it's just kind of flip the conditional and then put the other probability on there. And this shows up in the denominator, so it's part of the total probability. So plus given S times the probability of S. And then what else is down here? Well, so again, remember Bayes' rule is all about just extending this event of being marked as spam across the entire partition. And so this is going to be plus the probability of the positive marker given what? Well, given that it is spam is here, given that it isn't spam is the next one, right? Is the only other remaining option. All right, so again, this is another case where the partition just has two sets. All right, and then all of these numbers are actually told to us. So this would be 0.95 times 0.04, and then 0.95 times 0.04, right? So these two are the same. And this guy here we can see is 0.02, the probability of a positive mark, given that it's not spam, that's the false positive, that's 2% of the time, times the probability of S complement, which is 0.96. Okay, and then you can just crunch all these numbers, and you see 0.038 divided by 0.0572, and so we get 0.6643. All right. Very good. Very good. Okay, so we'll just do one more example. And this one is extremely wordy, so I'm going to actually just write out the facts and as we read through it. So a high school has 3 clubs. You got science, drama, and music. Right? So you got the science club, you got the drama club, and you got the music club. 30% of students are in the music club, and 50% of students are in drama, and 30% are in music, 50% are in drama, and 20% are in science. Shoot. I have this backwards. This is 30%, apologies, and this is 20%. Okay, so 30% are in science, 50% are in drama, and 20% are in music. So this is a 2. Okay. All right. Right, so you just got these 3 clubs, right? Now, the next thing, right, if a student is chosen at random, it's found that they did participate. So there's a spring competition, right, where the clubs are all kind of competing. If a student is chosen at random and it's found that they did participate in the school's spring competition, we are curious about which club that person is a part of. So what do we know? Well, we know that in the science club, 10% participated in the competition, right? So for science, 10% participated in the competition. Okay. And for drama, for the drama club, how many participated? 20% participated. Okay. And for music, How many participated? 40%. Okay, right? So you've got the science club, the drama club, and the music club. And 30% of the students are in science, 50% are in drama, 20% are in music. Now they had this big competition, and in that competition, if you were in science, 10% of them competed. And if for the drama kids, 20% of them competed. And for the music kids, 40% competed. Okay, so you got this kind of setup. So here's the question then. So if a student participated in the competition, what is the probability that they are in the music club? Okay. All right. And I think the idea is that every student is in one of these. So this is, it forms a partition of the student body, right? So you've got, all of your students, and you've got science, drama, and music. So maybe this is science, this is drama, and this is music. So everybody's in one of them, okay? And only one of them. It's partition. Okay, so let's figure out what we know. So the probability that you're in science, well, is 30%. Probability that you're in drama is 50%. And the probability that you're in the music club is 20%. So we've got those pieces. Okay. We're also told the participation numbers for all of the different clubs, right? And so we know that the probability that you competed, given that you were in science, was 10%. The probability that you competed, given that you were in drama, was 20%. And the probability that you competed, given you're a music student, is 40%. Okay. Now what we want to know is so we want the probability that you were in music given that you competed. Okay, so we know that you competed. What's the probability that you were in music? Okay, so you could kind of think of the overlaying set is the competition set. Right, so the picture kind of looks like this. So in this case, the partition is 3. The previous couple of examples, we just had partitions of 2. All right, so what are we interested in? We want to know the probability of M given C. And so we know that that'd be equal to the probability of C given M times the probability of M. And all of that is divided by the total probability. And so that's the probability of C given M times the probability of M. Plus, now again, it's just the probability of competing given a different piece of the partition. So the probability of competing given drama times the probability of drama. And then the probability of competing given science, times the probability of science. So it looks like that, right? And you're either in music, drama, or science, right? Music, drama, or science. And you want to know the probability of competing. Okay. And so we have all these numbers, right? They're all given to us. So 0.4 times 0.2 up top, and then 0.4 times 0.2 on the bottom, plus 0.2, 0.5. So this is 0.2, this is 0.5, and then this guy over here is 0.1 and 0.3. Okay, and so you can just do the math on that quick, and you will find 0.08 divided by 0.21, and we get 0.381. So there's a 38% chance you're in the music club, given that you competed in the spring event, the spring competition. All right, very good. So I think that's a great place to end this section. And then in the next video, we're going to get into kind of a gentle introduction to the idea of random variables and numerical events. So until then, take care.